So good afternoon, everyone. My name is Hanwei Yu, and today is my C3. I'm gonna introduce my PhD research work about novel electrode for enhanced selective lithium recovery from brine via capacitive deionization. My PhD principal supervisor is Professor Hokyong Shong, and co-supervisor is Dr. Guthrie Naidu, and external supervisor is Professor Tao He. Here is a brief outline of today's presentation. I will start with the research background, highlighting the importance of the lithium recovery and the potential of CDI, and then it's a brief literature review of CDI, and then it's my research objectives and thesis structures, followed by general experimental method, and then it's the main research works. Finally, it's in conclusion and publications and acknowledgements. First, about lithium. Lithium is often called the white gold in our current age. It plays critical roles in a variety of industries, such as batteries, ceramics, lubricating greases, especially the rapid expansion of the EV market and increasing reliance on the portable electric devices such as the mobile phone and laptop has become the main drivers behind the surging global demand for lithium. As the global technology continues to advance, the lithium consumption is booming. In 2012, the consumption was about 26,000 tons, but by 2022, it has surged to over 134,000 tons. It's more than 5 times higher, with a 41% jump in just 1 year. This sharp growth has also driven the price market of lithium increasing. Meanwhile, the lithium resources are unevenly distributed. The traditional method of lithium production is through hard mining, but currently it gets a lot of environmental concerns. It is non-renewable, it is chemical intensive, it's carbon intensive, and more importantly, the lithium ores is limited both in quantity and geographical availability. So where we can find more sustainable alternatives? In fact, about 75% of lithium on land is stored in brines, such as the solid brines and the geothermal brines. Even more strikingly, over 99.9% of global lithium reserve are found in the ocean. It is over 10,000 times more than all lithium resources on land. So these aquarium resources hold in a vast potential, but they also present two key challenges. First, it's a low lithium concentration. Second, the presence of competing ions such as sodium, potassium, magnesium, and calcium. And traditionally, the evaporation, solvent extraction, and absorption have been used, but they are slow and inefficient under such conditions. This had led to growing interest in emerging technologies such as electrochemical method and memory-based methods, which offer greater selectivity, scalability, and sustainability for lithium recovery from these complex aqueous resources brine. Among these, my PhD research focused on capacitive deionization, or CDI. It's an emerging and environment-friendly electroabsorption-based technology. So now let's talk about CDI. CDI has drawn increasing attention in recent years due to its simplicity, low energy requirements, and ability to operate under mild conditions. It's especially suitable for the low salinity environments, making it a strong candidate for select ion removal and especially lithium recovery. It's also allow for quick electrode regeneration, making it an efficient and reversible process. So how does it work? A typical CDI cell consists of two porous carbon electrodes separated by a spacer. When a low DC voltage is applied, the cations and anions migrate to the oppositely charged electrode and get temporarily absorbed. It's similar to how a sponge absorbs water. Once the voltage is reversed or removed, these ions are released back into solution, completing the whole cycle of absorption and desorption. So, and beyond the desalination, the CDI is also being explored for other potential applications, including the energy harvesting, the water purification, and the resource recovery, including lithium recovery. Now, I'd like to give a brief literature review of CDI and walk you through the development timeline. The concept of capacitive deionization was first introduced in 1960s with the invention of the flow-by CDI architecture, where the feed water flows between the two porous carbon electrodes. Later in the 1970s, the flow-through CDI concept was developed. And however, there's a long period of limited research activity until the mid-1990s, when the carbon algae materials were applied to CDI, reviving interest in this field again. In 21st century, CDI research gained more significant momentum, leading to the emergence of the multiple advanced architectures, such as the MCDI, HCDI, invented CDI, FCDI, and so on. When it comes to the lithium recovery, CDI research has mainly focused on two key directions, which is material synthesis and electrode fabrication, which is also my focus on my PhD study. And another one is process enhancement through the operation mode adjustment, such as constant current or constant voltage, and so on. In CDI system designed for lithium recovery, the electrode material is one of the most crucial roles. It can determine the absorption performance and the ion selectivity. The current research focused on CDI material, mainly focused on the carbon-based material, the battery-type material, and polymer or membrane-based materials. And for further enhancing performance, various electric modification strategy has been explored, including surface functionalization, the doping method, and the composite method, and some nanomaterial incorporation. Through the literature review, I identified the foundation of my PhD research, which is there are three promising strategies that can potentially enhance lithium selectivity in CDI electrodes, which is the size-sieving effect, the Donnan effect, and the memory effect. Building on these three strategies identified from literature review, my PhD research aimed to explore from these three different mechanisms for enhancing lithium selectivity in CDI system. So based on first strategy of size-sieving effect, the objective is to modify activity carbon electrode with morph material that have the sub-nanoscale channels to investigate whether physical ion size exclusion can improve lithium selectivity. So, and mechanism 2 involves functional group affinity and the Donnan effect. And I will develop and code self-knitted membrane on AC electrode to evaluate this mechanism. And mechanism 3 is the memory effect of the lithium ion sieves. And I will fabricate the LS-based electrode to investigate this mechanism. Based on the research objectives, here outlines the overall structure of my thesis, which includes the background, the introduction, literature review, general experimental methods, and the main research, including the just mentioned 3 strategy-based research work, and finally, it's a conclusion and recommendation. Now, I would like to introduce the general experiment setup and method used through my research. The CDI setup consists of a DC power supply, a CDI cell, a pump to circulate the feed solution, and a multimeter to monitor the conductivity and pH. And the CDI cell is composed of 2 graphite-supported electrode, a spacer, and ion selecting membrane, and AEM active carbon electrode. And the electrofabrication method used in my cathode fabrication, including the in situ growth, deposition, casting knife, and deep coating. The key parameters used to evaluate the CDI performance, including the removal rate, which tells us how much of a specific ion is absorbed during absorption step, and the gross lithium selectivity, also lithium absorption selectivity. It reflects the relative absorption preference of lithium over another competing ion. In contrast, the overall lithium selectivity captures the entire CDI process, including absorption and desorption. That means GLS shows how selectivity lithium is absorbed, while the overall lithium selectivity tells us how well lithium is retained and separated through the whole process. And now I'd like to introduce my first strategy of my research, enhancing lithium selectivity, use a size-sieving effect. In this strategy, I modified the commercial active carbon electrode with ZFA type of morph. ZFA is a promising material for ion separation thanks to its substantial surface area and the sub-nanoscale pore windows. Its separates mechanism is based on the size-sieving effect. ZIF8 has sub-nanoscale pore windows. If we compare this parameter with the hydrated and dehydrated, the ion radii of lithium and its main competitors, we can find the dehydrated ions are smaller than the ZIF8 windows, but the hydrated ions are too large to pass through without dehydration. So under an applied electric field, cations are partially dehydrated to the ZIF8 interface, which allows them to enter the pores. Once inside the cavity, they rehydrate and must dehydrate again to exit to reach the carbon layer. So because lithium has the lowest dehydration energy, it passes through more easily and quickly than other competing ions. This difference in transport efficiency due to the hydration and dehydration process leads to the effective size-based ion separation. So in this research on the commercial AC electrodes, I I coated the ZIF8 type of MOF on it. First, compare with it's used by using the water-based in situ growth method. A double layer of ZIF8 was coated on electrode. However, because due to the poor hydrostability of ZIF8, to enhance the water stability, I incorporate polydopamine to enhance the ZIF8's hydrostability. I use the deposition method to coat a layer of ZIF8 polydopamine membrane on AC electrode. And the test condition was a flow rate of 20 milliliter per minute, and the model solution for the feed is a binary solution containing lithium and another competing ions. Now let's start with the characterization results. From the SEM image, we can see the morphological difference between the bare AC electrode and modified electrode. So the ZIF8 is uniformly grown on the AC electrode surface. And then after soaking in water, we can find that the unmodified ZIF8 shows the structure change, but the ZIF8 polydopamine membrane still can retain its original structure. It confirms that the PDA incorporation improves the water stability. And then let's see the BET result shows the surface area of ZIF8 and the ZIF8 polydopamine. The ZIF8 surface area is significantly larger than ZIF8 polydopamine, but this trade-off is necessary for membrane durability in aqueous systems. The FTIR results confirm the successful coating of PDA by showing the characteristic peaks. Finally, the XRD patterns also illustrate the crystal structure of the material, and also confirms that after soaking, ZIF8 polydopamine still remains its typical peaks. Now let's see the CDI performance of using these electrodes. So using the AC electrode, the absorption selectivity of lithium and sodium is 0.73. For lithium, potassium is 0.43. Lithium, magnesium is 0.67, and lithium for calcium is 0.58. After coating ZIF8 layer, we can find that the presence of the ZIF8 coating substantially improved the lithium selectivity over monovalent ions. But the high charge density of divalent ions and the ZIF8 conductivity can lead to the competitive absorption, blocking the lithium ion transport. And after modifying with the ZIF8 polydopamine, we can find that the lithium removal rate and lithium selectivity increased in monovalent cases. And the presence of the ZIF8 polydopamine built up the preference of electrode to divalent ions. Here's the comparison of CDI performance among these different cathodes. We found the ZIF8 layer promotes the selective passage of small monovalent cations via the size-sieving effect. And in mixed ion systems, the divalent ions dominate due to the stronger electrostatic forces on the electric field. And the F8 polydopamine coating improved the water stability, but compromised the lithium selectivity due to large pore size. And here's a key trade-off. Lithium selectivity and water stability must balance in membrane design. Then I also did a CDI test using AC-Z-phase polydiaphragm electrode under different applied voltage, and I compared the energy input ability, and I tested the lithium absorption capacity, charge efficiency, and energy normalized to lithium as a metrics to evaluate the performance of CDI. I found that the applied voltage demonstrate negative relations with lithium selectivity, charge efficiency, and lithium normalized to energy normalized to lithium. And the trade-off is the slightly lower lithium absorption capacity under the lower applied voltage. Here is a brief conclusion of this part the research work. In this research, I investigated strategy 1, that is enhancing lithium selectivity in CDI via morph-based size-sieving, and I synthesized the phase-based AC electrodes and use PDA as adhesive for improved hydrostability, and conduct a CDI test using binary solutions. And the key finding including the AFIT and ZFIT PDA modification improved the lithium selectivity in monovalent systems. Lower voltage favors high selectivities, charge efficiency, and energy normalized to lithium. The poor performance in lithium, magnesium, and lithium calcium due to the valence effects and dehydration in energy. Here are some limitations in this research. I used the binary ion system. It cannot reflect the real-world brine complexity, but it's only for compare the lithium and its main competing ions. And the coating process need to be keep optimized for long-term use. And the CDI evaluation this time, I only focused on the absorption, neglect the desorption, which is gonna be improved in the next research work. So in the second research work, I used the second strategy, enhancing the lithium selectivity through the Donnan effect by integrating functional membrane onto CDI electrode. So to implement this approach, I fabricated a series of sulfonated membrane called SPK membrane and coated them on the commercial AC electrodes. The sulfonated group on these membranes introduced the fixed negative charge, which can facilitate the selective absorption via the Donnan exclusion mechanism. And 3 types of SPK membrane based on their sulfonated degree was fabricated, which is SPK 20, 40, and 60. The test condition is followed the same way with the last research. The characterizations can confirm the successful fabrication and physical properties of the ACSPK electrode. And SEM image shows the surface and the cross-section morphology of electrodes. As the sulfonation degree increase, the coating appears more compact and uniform. And for the water contact angle, we can see that as the sulfonation degree increased, the contact angle decreased, suggesting enhanced surface hydrophility, which may benefit the ion transport. Additional, the the water uptake test show increased water absorption with large sulfonation as well. Here is the CDI performance using AC-SpK20 electrode. We found the divalent ions have stronger interface with the sulfonated groups occupying more binding sites, and this binding lithium transport and interaction with sulfonate group. And with the AC-SpK40 electrode, we found more sulfonated group can enhance lithium selectivity in divalent systems, but also increase the binding strength, which hinder the lithium desorption in presence of the divalent ions. This is the result using the AC-SpK60 electrodes. The first increase in sulfonate group enhanced the divalent ion capture, but significantly hinder lithium desorption in the divalent cases. So here is a comparison of CDI performance among SPK 20, 40, and 60. After SPK coating on AC electrode, lithium removal rate and lithium selectivity in lithium potassium feed improved by up to over 200 and over 150% respectively. And the SPK membrane demonstrate a preference for capturing and releasing divalent ions. And the impact of sulfonate degree has very minimal impact in monovalent cases, but noticeable effect on divalent cases. And here is the based on the desorption result. Here is a comparison. So the recovery rate values higher in monovalent cases, and sulfonation degree has a little effect on recovery rate in monovalent cases. High sulfonation significantly lower recovery rates in divalent cases because the stronger binding between the sulfonate group and divalent ions can hinder the lithium desorption. And the recovery rate could improve with may improve with the higher desorption voltage, but it will have the trade-off with the energy consumption. And the figure shows the CDI ion transport process with the SPK membrane. First, step one is the electromigration. The cations migrate to membrane surface under the electric field and form an electrical double layer. And then some cations bind to sulfonate group inside the SPK membranes. Divalent cations show stronger binding affinity. Remaining cations pass through membrane to reach active carbon layer, absorbed in pores and interparticle spaces. And finally, most absorbed cation leave the active carbon and re-enter membrane. Partial bonds between sulfonate group and cation break, and then cations released into the effluent. But some cations rebind in the membrane, so trapped in the AC membrane electrode. And we found the desorption efficient. It can depend on the applied voltage strength and the cation binding affinity. Here is a brief conclusion of this research. In this research, we investigated the strategy 2, which is enhanced lithium selectivity via functional group affinity and the Donnan effect. The 3 type of SPK membrane was used to modify the AC electrode, and the CDI performance was the test using binary solutions. The key findings include the CDI test shows the improvement in lithium removal and selectivity compared to the bare AC electrodes. And lithium potassium system shows the best performance among monovalent cases. Sulfonation group degree has a limited effect in monovalent cases, but strong impact on lithium recovery in divalent cases. So next, let's move to the strategy 3, which is lithium extraction via memory effect extraction using lithium INC-based CDI. First, let's see what is the memory effect of lithium adsorbents. Mainly there are 3 types of the metal-based adsorptions which has the memory effect, which is aluminum-based, manganese-based, and titanium-based lithium adsorbents. And aluminum-based adsorbent is more mature and has been used in industry, but it shows the lowest lithium capacity and selectivity. And the magnesium-based adsorbent has a high selectivity, but the manganese leaching has the risk to damage the environment. The titanium-based adsorbent has a high capacity, but it is not fully researched as other 2 types of adsorbents. And also the performance declined after the conventional granulation, and it's hindered its scale-up research. So in my research, I chose the titanium-based adsorbent and use it another way in CDI rather than traditional granulation method for the selective lithium recovery. And here is material and method. The ion selective layer was fabricated using the lithium tantalate and polymer called EVA. The EVA contains the PVA and the PE parts, which one side is hydrophilic and one side is hydrophobic. So one side can provide the strong structure, and another side can provide the contact with water that benefits the ion adsorption. And in this research, the FIT solution, we used the simulated seawater desalination brine based on the literature results. And the CDI process is a little bit different with the previous method. After the adsorption process, we introduced a rinsing stage before the desorption stage to rinse out the competing ions, because the lithium can be intercalation into the LTO structure, but other competing ions mainly only temporarily adsorbed on the surface of the electrode. So the rinsing stage has a possibility to firstly remove the competing ions that improve the lithium selectivity after desorption. In the characterization, the XRD confirms the LTO structure, and the SEM image shows the LTO particles and the uniform polymer coating of the LTO layer on the AC electrode on the graphite sheet. And the water contact angle test can show that the incorporation of EVA binder enhance the hydrophility and improve the adsorption kinetics. So before the CDI test, we did the LTO powder absorption test, which is based on the effusion. The results shows that the lithium capacity based on the diffusion is pH dependent. On the alkaline condition, the capacity can reach to 9.8 milligram per gram, but in the neutral condition, it is much lower. And then we find the high lithium selectivity across all coexistent ions, especially magnesium. And neutral pH actually can facilitate the lithium recovery. And then we also did the electrochemical test. The CV test shows the LTO membrane has a feather-like the behavior, which shows the lithium intercalation activity. And after the cooperate with graphite sheets, the CV curves shows the high current and electric double layer-like profile. And the GCD test shows at the low current, it shows the stable symmetric curves. But at the high currents, it's limited by the ion diffusion resistance. The PCD result test shows the stable current response over 8 cycles, and it indicates excellent electrochemical stability and fast ionic kinetics in low concentration lithium. Now is a result of the CDI performance. We can see that around 60% of lithium in the phase solution was absorbed by the CDI system, and the pH has a minimal impact on lithium selectivity after using the CDI method. The gross lithium selectivity over competing cations are ranged between 10 to 20, but due to the rinsing stage, the final active lithium selectivity increased dramatically to over 200. We also did a 10-cycle CDI stability test, and we found that the current density, pH, and conductivity remained stable over 10 cycles, and the extended rinsing in early stage improved selectivity by removing weakly absorbed ions. Overall, the selectivity value remains high and all exceeding a factor of 100. Here's the brief conclusion of this research. In this research, I developed LTO membrane-coated electrode via deep coating and evaluate its CDI performance using the simulated seawater desalination brine. The key findings include it achieves selective lithium recovery at neutral pH, and the CDI system achieved a very high lithium selectivity. The rinsing stage critically enhanced the lithium selectivity. The electrode remains stable over 10 cycles, and it emphasized the importance of lithium recovery data, not only just electrochemical signals in stability evaluations. And for the future direction, after my PhD, we can optimize the lithium-ion sieve membrane design for better selectivity and durability, and we will investigate for scalability and real seawater desalination brine compatibility, and targeting suitable, selective, and scalable lithium extraction for the real-world development. Here is a final conclusion of my PhD research, enhancing lithium selectivity in CDI. The size-sieving via modified electrode, the Z-fate-coated AC electrode significantly improved lithium selectivity in monovalent cases at low voltage. The performance declined in divalent ion environments, revealing the limitation of size-based separation. And the strategy 2, the functional group affinity and Donnan effect with SPK membrane. It shows the SPK integrated electrode has a moderate improvement over barrier AC electrodes, and the effectiveness limited by external electric field, weakening the Donnan effect. And in the strategy 3, memory effect of LTO-based electrodes, we found LTO cathode enable high lithium selectivity and stable performance. Rinsing stage can prove critical in enhanced selectivity. So this is my research work in my PhD study, and I had 11 publications, including 5 of the first author papers and 5 co-author publications. And I attended 7 conferences. Finally, I would like to have the acknowledgement. I would like to thank you, my supervisor, Professor Hokyong Sheng, my co-supervisor, Dr. Gayatri Naidu, my external supervisor, Professor Tao He, and today's panel chair, Associate Professor Sharab, today's assessor, Associate Professor Leonard, and Dr. Yang Wu. And I would like to thank my senior colleagues that gave me a lot of help, Dr. Chen Wang, Dr. Mukit, Dr. MJ Park, and Dr. Andrea, and also my peer and junior colleagues, Maxun, Dai, Qian Chen, Yeshi, Gayas, Said. And this research, thankful, and finally thank all the fundings for my PhD research. That's all. Thank you everybody for listening for my C3.